Okay, today we're going to be talking about Simon's algorithm. Now, Simon's algorithm is pretty exciting because it's the first time a quantum algorithm demonstrates a full complexity class advantage over its classical counterpart. In other words, a quantum algorithm can now solve a problem significantly faster than a classical algorithm. This kind of demonstrates quantum supremacy for one of the first times. Actually, it is the first time. Historically, it was the first algorithm that showed that there was this very, very difficult classical problem, which is the problem that we're going to be solving here, and it could be only solved at exponential time on a classical computer. That means that as the input to the algorithm grows, let's say n is the size of the input to the algorithm, the amount of time and memory and resources that it takes to compute this algorithm will grow exponentially. Now, exponential functions grow really fast. In fact, they're the fastest growing functions. That's really bad for a classical computer. Because it means when we want to compute big things, it's just not possible. We can't do it with too big of inputs. And with a quantum computer, on the other hand, Simon showed that this algorithm could compute it in polynomial time. That's a full complexity class reduction, and that's huge. So, what's the problem that we're going to solve here? Well, Simon's problem involves, again, a function, as all of these circuits have so far, right? Um, this is a function with a very special property, however. It's a function with the property that it has a period. F of x equals f of y. That's its period. In other words, it comes back to the same value after a certain period of time. But x and y have a special relationship. Y specifically will only demonstrate this periodic behavior if x or bitwise x or s is equal to y. So if x times this kind of like mystery string here, x or bitwise times this mystery string here is equal to y, then f will take on the same function. So you can kind of think about this as a periodic function in bitwise terms. What is this x or operation? Well, first off, s, x, and y are all or all n-bit strings. And this notation kind of just means I'm picking out n zeros or ones. This is kind of this possibility space of values it can take, and n is the number of dimensions of the space. So there's going to be n either zeros or ones. So let's say let's say we choose n to equal 2, then x can be that, where that's not 10, that's 1, 0 in binary, right? So if n is equal to 4, if n is equal to 4, y can maybe just look like that, right? That's kind of what we're talking about. All right, so what does this XOR do? It's a bitwise exclusive OR operation. I don't want to say gate. Let's say we have these. Yeah, let's set this equal to x, and let's set this equal to s. And we want to bitwise exclusive OR them. If they are different, in other words, if it's 1 or 0, then it's 1. And to make this more intuitive, let's say 1 is true and 0 is false, because in Boolean logic it is. So true or false is true. So if one or the other is true, then it's true. But both can't be true. That's the exclusive. That's the X part of this exclusive OR. So 0, 0, that's false because they're both false. 1 or 0, it's or. If one or the other is true, then we're golden. So one or the other, right? So that's the exclusive OR, and that's going to be equal to y in this case, right? Okay, so this that's what this function does. And we really, really, really want to find out what x is. We're quite curious about this. So how do we do that? Um, Generally, how would you approach this problem? Um, well, the way to do it classically is you have this kind of like black box where the function is, and you input values to it. So you would input a bunch of zeros and ones, and you would try to find when f of x is equal to f of y. That is, you would try to find the inputs that are periodic. And through that kind of trial and error process, you would eventually find S. Because a property of the bitwise OR, exclusive OR, is that this is also true. x plus bitwise or y is also equal to s. So if we find a bunch of strings like zeros and ones like x and zeros and ones like y that are periodic like this, we can XOR them together and eventually find s. Um, that's the good news. The bad news is that this is going to take an exponential amount of inputs, where n is the number of bits that are involved here, right? So that's not so great classically. In fact, when you're dealing with n-bit strings, 2 to the n is what we're going to be dealing with here. So you can see this kind of blows up very, very quickly. Why 2 to the n? Well, because when you have n possible spaces, and each one can take a 0 or a 1, this is the number of combinations, permutations, that you can have. Or maybe it's this, right? 2 to the n. So you kind of have to trial and error this out classically. And that's not great. That's a lot. But surprise, surprise, with quantum parallelism and the quantum circuit I'm going to show you in the next lecture, we're going to see how to do this much more efficiently. But first I want to talk a little bit about complexity theory and why it's so monumental that this can do this so much faster in exponential time versus polynomial time. So let's say we have this computer here, and we have another computer here. And we're computer scientists, and we're really interested in coming up with a theory of how hard is a problem to compute. So if I have a problem and I have an algorithm that solves that problem, how complex is that algorithm? How many resources does that algorithm take? Maybe that's a better question. How many resources does it take? How much time does that algorithm take to execute on your computer? How much memory does that algorithm eat while it's executing? So I have two different computers. The problem is it's going to be a different answer for each of these different computers. Let's say I want to reverse a string. Some computers are better at that than other computers. It depends on the chipset. Even modern computers that are universal computers, the instruction set of the CPU will make some computers slightly faster than other computers. Um, so we kind of need a more heuristic way to say when an algorithm is hard and when one is not, because we do not want our classification of a software algorithm to depend on the hardware computing device. We want it to be substrate independent, if you will. Otherwise, it doesn't really make any sense, right? Because we're talking about then how good is your computer versus how hard is the problem. So how are we going to do something like that? Well, it turns out, and this was kind of just found, that if you have a function like x squared plus x plus 5, something like this, and you kind of just where this should really be n actually, because n is the size of the input, right? Let's say you are you have a string of how many ever bits, and you want this thing to reverse that string for you. 0 1 0 1 0. Oh, I think I found a palindromic string. Okay, so you want it to reverse that. And you find that the function is 5n squared plus 4n plus 2, where 2 is just, I don't know, some bootsteps or something like that. So on this computer, maybe it's a little bit different. Maybe it's like this. The chipset's just a little bit more efficient at reversing strings, that's all. And it's got one less bootstrap. Um, so how it turns out that if we take n to infinity, then asymptotically, these are both the same. They're both of order n squared. So we can do it in quadratic time, polynomial time, because that's a type of polynomial. So this is a p-class problem. We would call it a p-class problem because it can be done in polynomial time. If instead these algorithms were asymptotically exponential, we would call it an NP problem, not polynomial, and we would say it is done in exponential time. Now that's the difference we're talking about here with Simon's problem. That's the quantum advantage. Classically, on a regular computer, like your laptop, the problem that we just described is solved in exponential time. Whereas with Simon's algorithm on a quantum computer, we can solve it in polynomial time. So that's a huge speed up, a massive advantage, and it demonstrates clear quantum supremacy. Clear impetus to build a quantum computer there. So next time I'm going to show you the quantum circuit of how Simon's algorithm actually works, and we'll talk about how quantum parallelism and phases, and of course there will be Hadamard gates, are going to give us this speed up, and it's for the first time a quantum algorithm will show true quantum supremacy.